Now we could also do the exact same thing for a capacitor that's discharging. We wouldn't need a battery in that circuit, would we? We would just need a charged capacitor. So let me write over here. This is all for charging. And now we're going to do a capacitor that's discharging. So our circuit, we would need a capacitor, we would need a resistor, and we don't need anything else, right? We need a switch. And the capacitor starts charged up. And what we get here, if we did the same, treatment, if we went around using the loop rule, came up with our differential equation, solved it, we would get this. We would get Q as a function of time. Well, first let's look at what happens. Let's look at the graphs here. The charge on that capacitor as a function of time, it starts out at Q max, and then it decays after a long time, it goes to 0. So what we get Q as a function of time is going to be Q max, which is just, I'll just write Q max. That's C times whatever voltage charged it, right? But I took the battery out of the circuit. So I'll just write Q max, and that's e to the minus t over tau. So we don't have a 1 minus e to the minus t over tau. It's just e to the t over tau. Let's see if that makes sense. At t equals 0, this is just 1. E to the 0 is just 1. So we get Q maximum. At t equals 0, we get Q maximum. As t goes to infinity, we get a 1 over e to the infinity, which goes to 0. So Q goes to 0 as t goes to infinity. So that makes sense, right, if we're discharging our capacitor. So just do a quick check with the t equals 0, t equals infinity. Make sure you have the right equation. Are you charging or are you discharging? Okay, so this is the same type of thing. Tau is equal to RC. And if we know the values of R and C, and you knew how much charge was on the capacitor initially, I could ask you how much charge is on the capacitor after, 4 milliseconds after I close that switch, something like that, and we could figure it out. Okay. So those are RC circuits, and the whole idea there is that there's some time lapse as we charge and discharge these circuits. It doesn't happen instantaneously. And as the charges move, they interact. And the reason charges move at all is because that capacitor is like a big reservoir. And as we move charges around, it can take up some of the slack in the wires, right? Some of the excess electrons as we move them. And so it can actually get some current to flow, even though it's technically an open circuit. But that current doesn't flow for very long, right? After a very short period of time, it stops because the excess storage space in our reservoir, in our capacitor, is used up, and then the flow stops. But during those very short time, during those milliseconds or so that charges are moving, interesting things can happen, and so we want to look at that. It also leads us into AC circuits that we're going to talk about later in the quarter. The idea there being this voltage, instead of always trying to push the charges in the same direction, the source alternates. So for a very brief amount of time, the battery is oriented in one way, like this, and charges begin to move and build up on the capacitor, and then the polarity switches, and the charges go in the opposite direction. And then it switches back, and they go in the other direction. And if we switch fast enough, or if the capacitor is big enough, I guess either way, then the charges don't really mind the fact that there's a capacitor in there. They start to flow before the capacitor builds up the charge. Because it's big enough, the voltage switches and the current starts to go in the other direction. And what we'll see is that it's almost like there's not a capacitor in the circuit if we're switching fast enough and the capacitor is big enough. If we're switching slowly or the capacitor is small, then it does affect the charges, right, the flow of charges. So we'll learn about that more later, but I wanted to lead into what we'll get to with AC circuits. All right, so RC circuits. Charging or discharging, we've got this equation that tells us how the time dependence of the current or the charge on the capacitor either way. All right, so let's do one more worksheet with series and parallel capacitors. So why don't we make this 12-volt batteries and find the charge on each of these 6 capacitors. 12 volts, right? They're all in parallel with the battery. 12 volts. And so what do we get? 12 microcoulombs. And how about E? Two times 12. And D, it's going to have 3 times as much charge as the first one. Okay, all 3 of those are hooked up to the same battery, same potential difference. And the total charge stored in that system is what? You add them all up, right? Is it 72? 72. Okay, how about the next one? When they're in series. What's the thought process here?